Hi guys, welcome back to my physics class. Yeah, I hope you have done your lab exams well. Okay, so today I have taken almost the complete SI units and the differences in your second PUC physics. Okay, so I've taken like complete SI units. Let's see. In case if I've missed any, please drop it in comment box. Okay, if you're watching this channel, please like, share, and subscribe, and follow our channel for your exam preparation. So yeah, let's start now. So yeah, charge. So yeah, you can just solve along with me. Yeah, so what's a charge SI unit, guys? The charge SI unit is Coulomb, right? So Coulomb, and in brackets you get capital C. Okay, and then current SI unit is Ampere. Okay, as you know, it's a name of a scientist, so we denote it by capital letters. Next, current density. So what's the current density formula? Current is I, right? Current density is current per unit area. So SI unit of current is area. SI unit of current is ampere, per SI unit of area is meter square. Therefore, SI unit of current density is ampere per meter square. Okay, where current density is denoted by letter J. J equals I by A. Next, electric potential or voltage or potential difference. So SI unit is volt. Next, SI unit of resistance is ohm. So we denote it by ohm. And what about the SI unit of resistivity? Where resistivity is denoted by rho. Rho equals RA by L. So you know this formula. So using this formula, when you substitute ohm meter square by meter, you get SI unit as ohm meter. You would have already used in your lab exams. So you might be knowing this. Next, conductivity. So what is this conductivity? Conductivity is denoted by sigma. So conductivity is reciprocal of resistivity. Okay. So if resistivity is ohm meter, therefore conductivity will be what? It will be per ohm per meter. Okay. Instead of per ohm, we can write it as Simon, guys. Simon per meter. Okay, so the other word for per ohm is what? Simon, S-I-E-M-E-N. So we can write it as Simon per meter as SI unit of conductivity. Next, SI unit of electric dipole moment. So electric dipole moment formula is what? P equals Q times 2A. So SI unit of charge is Coulomb, whereas SI unit of distance is meter. So SI unit of electric dipole moment is what? Coulomb meter. Okay, so you might get all these SI units in MCQs or 1 mark like these type of questions. You might get it, and you will get it. At least one question you will get it. Okay, so that's the reason I've selected almost all the SI units over here. Next, what is the SI unit of magnetic dipole moment? Where electric dipole moment is Coulomb meter, right? So here magnetic dipole moment is, instead of Coulomb take ampere, instead of meter take meter square. Therefore, SI unit of magnetic dipole moment is ampere meter square. Okay, so then moving to the next. So SI unit of electric field, guys. SI unit of electric field is Newton per Coulomb. Okay, so it is, or volt per meter also we can take it. Okay, because in options, if they have not given Newton per Coulomb, and if they have given volt per meter, you can take that volt per meter. Okay, and then SI unit of magnetic field or magnetic induction is given by Tesla, guys. Okay, so capital T. Next, SI unit of capacitance is Farad. F-A-R-A-D, and in brackets you get capital F. And next, SI unit of electric flux, where we know electric flux is given by the formula E times EDS, right? Electric field into surface area. So that's the reason its SI unit is Newton per Coulomb, and surface area is meter square. Okay, so you can take Newton meter square per Coulomb. Next, SI unit of magnetic flux. What is SI unit of magnetic flux? Directly you can take it as Weber. Okay, W-E-B-E-R, capital W. Next, SI unit of inductance or mutual inductance or self-inductance is given by the formula Henry. Okay, so H, capital H. Next, magnetic permeability. Okay, so what is the SI unit of magnetic permeability? It is ampere per meter. Okay, so it is the magnetic permeability. Sorry, I missed permittivity also. Okay, so sorry, 1 minute. Okay, so SI unit of permittivity is what? SI unit of permittivity is where we get this permittivity. We get it in Coulomb's law formula, right? So we get like F equals 1 by 4 pi epsilon naught Q1 Q2 by D square. So if I take epsilon here and F here, so I'll get 1 by 4 pi F. So what will be the epsilon naught SI unit? Charge into charge, that is Coulomb square per, force is in the denominator, so Newton per, and distance square per meter square. So this will be the SI unit of permittivity. Okay. Next, what is the SI unit of magnetic permeability? You can take Henry per meter. Okay, so that's a SI unit of magnetic permeability. Next, what is the SI unit of magnetization or magnetic intensity? It is ampere per meter, guys. Okay, and then SI unit of impedance, or inductive reactance or capacitive reactance, it is denoted, it is given by ohm itself, because they all are resistance. Okay, so that's the reason impedance is denoted by Z, right? And inductive capacitance or capacitive reactance or inductive reactance, so that's denoted by XL and XC. So they all the SI unit is ohm. Okay, so I think this much I've selected. Okay, so in case if I've missed any, please drop it in the comment box. Okay, so for you people to solve, I'll give the SI unit. Okay, so find out what is the SI unit of mobility, guys. Okay, so if you know the answer, please drop a message in the comment box. Okay, so that's a work for you. Fine. Now let's move to the next thing, that is differentiate. Okay, so we have like I've selected around 10 differentiate questions. Okay, it can be asked for 2 marks or 3 marks, but confirm one question, you will get it from this, and it's very simple also. So easily you can score marks in this. Okay, now we have a differentiate between polar and non-polar molecules. Okay, see, polar means something which comes to our mind is what? Polar. Polar means something like related to water, right? So in that way you can connect it. So polar is what? It is something related to water. Let me take it as water. Water is denoted by H2O. Okay. Fine. So water is H2O. Okay. So here you can see there are two elements like hydrogen and oxygen. From this we can say that there is a permanent dipole moment. Okay, so polar molecule will have what? Permanent dipole moment. Okay, so that can be the first difference. So using this H2O itself, you can say they have a permanent dipole moment. Okay, and then you can say that center of positive and negative will not coincide. Okay, the center of positive charges and the negative charges will not coincide. Why? Because they have a permanent dipole moment, and it's a combination of two elements, H2O. Okay, in that way you can take these 2 points. Example, you can write H2O, CO2, NH3. All these examples will come under what? Polar molecules. Okay, next coming to the non-polar molecules. Here only one element will be taken, like oxygen, O2 or N2 and so on. Okay, since there is only one element, we can say that they don't have any permanent dipole moment. Okay, because of course there should be two molecules, right, to have a permanent dipole moment. So that in like that you can connect it. Okay, so in this case we can say they don't have any permanent dipole moment, and also we can say that the positive center of positive charges and negative charges will coincide here. Okay, there it was not coinciding because they had a permanent dipole moment, but here it is coinciding. Okay, that's the reason we say that what center of positive and negative charges will coincide, and therefore write the examples. That's it. Okay, it's a very simple question. Instead of differentiate, they can ask us what are polar and non-polar molecules, give examples. In case if they ask, just write these points and write the examples. Okay, I hope you understood this. Fine. Now let's move to the next question. Current and current density. Okay, it's not very much expected question, but still we can learn this. Okay, so current, we know what is a current. The current is what? Rate of flow of electric charges. Okay, but what is current density? As I mentioned in SI unit, current density is denoted by J. J equals what? Current per unit area. Okay. So current per unit area. So you can say current per unit area of cross section is given by current density. Okay, and also we can say that since we can see here current density is depending on area, but it is not depending on any area. Okay, it will not depend on an area of cross section. So that's the reason we can say it is independent of area of cross section, whereas current density depends on area of cross section, and SI unit is ampere, whereas SI unit is ampere per meter square. And finally, one it's a very common differences, that is current it is a scalar quantity, whereas current density is a vector quantity. Okay, so these are the differences. Next, moving to the next, that is EMF and terminal potential difference. Okay, again you might have learned this, you have already done the lab. So in this lab we have mentioned EMF and terminal potential difference, right? So in that way we can say potential difference is a what? It is of a cell in an open circuit. Okay, but whereas a terminal potential difference, it is across a cell in a closed circuit. So that's the reason we use the two different quantity, that is EMF and terminal potential difference. Okay, so EMF is nothing but electromotive force. then it is independent of external circuit, because you might have seen we take EMF and internal resistance, that is within the cell we take it, right? So that's the reason we say it is independent of an external circuit. Okay, but terminal potential difference, it depends on a current drawn. Okay, it will depend on what current is drawn from the battery. Okay, and then yeah, it is greater than terminal potential difference, whereas terminal potential difference will be less than the EMF. Okay, so these are the small differences. Fine. Next, differentiate between para, dia, and ferromagnetic materials. Most expected question. Okay, so I think it can be asked as differentiate also, or they can ask you explain the three different magnetic materials also. Okay, so we have like diamagnetic material, paramagnetic material, and ferromagnetic material. Okay, so based on their property, I have listed three materials over here. Sometimes I might ask you any two differences, like they might ask you differentiate between dia and para, or para and ferro, or dia and ferro, anything they can ask you. So here I've listed, I've taken all the three materials. Okay, so first dia, the name itself tells, okay, diamagnetic is something, it will repel the magnetic materials. Okay, I mean it will repel it. Okay, repelled by the magnets. Whereas paramagnetic materials are, it is weakly attracted, not very strongly attracted, it is weakly attracted by the magnets. Okay, so whereas ferromagnetic materials are strongly attracted by the magnetic materials. So in that way you can think dia means repelling, okay, para means weakly attraction, whereas ferro is ferro, the name itself tells ferric. Okay, so ferro is strongly attracted by the magnets. Okay, then moving to the, this is a behavior in a magnetic field. Next, moving to the magnetic permeability. Permeability is very less than 1 over here. Okay, so permeability we can take it as mu r. Permeability is less than 1. Here permeability is slightly greater than 1, whereas here it is very much greater than 1. Okay, so that's the differences. Remember, permeability is lesser than 1. Here permeability is greater than 1, whereas here it is very much greater than 1. The value will be more than 1, like that. Okay, next up, magnetic susceptibility. Okay, so magnetic okay, so the magnetic susceptibility is low and negative. Okay, whereas here it is low and positive, and here it is very high and positive value. Okay, since it is low and it is negative because it's repelling, right? So it is low as well as negative, whereas here it is low and positive, but here it is low and strong, it is high, it is. Okay, very high and positive it is. Okay, fine. Now susceptibility, it is independent of temperature in a diamagnetic material. Okay, remember this. Whereas in a paramagnetic material, susceptibility is reciprocal. Okay, it will inversely vary with the temperature. Whereas here in ferromagnetic material, susceptibility depends on the temperature. Okay, so this much about the temperature you can remember, the properties related to temperature. Okay, now coming to the magnetic field lines, how it passes in case if there is a magnetic material and I'm applying a magnetic field. So what happens is, if I place a diamagnetic material over here and if I allow the magnetic field lines to pass through it, they will not pass through them. Okay, they will go like this. That means they will be expelled out from the magnetic field. Please remember this. Okay, they will be expelling out from the magnetic field. But in case of a paramagnetic, if there is a paramagnetic material and if I allow the magnetic field lines to pass, yes, few of them will pass through it. Okay, but in case of a ferromagnetic material, if I allow the magnetic field lines to pass, every line completely it will pass through the ferromagnetic materials. Okay, so please remember this, and it's a very simple point. Okay, then coming to the example. Okay, so diamagnetic material example is like, see, diamagnetic is what it will repel. Okay, see, I think we like women is mostly attracted towards the gold, diamond, and all, right? But dia is something which will repel. Okay, so the example for dia in that way you can think. Okay, the diamond, gold, silver, diamond, all these are examples of what, diamagnetic materials. Okay, so women is strongly attracted towards diamond, gold, silver, but dia is something which will repel. That's the reason the example of diamagnetic material is gold, silver, diamond, like that you can consider. Next, paramagnetic material, yes, sodium, calcium, platinum, all these comes under the paramagnetic material. And again, as I said, the name itself tells ferro. Ferro means what? Iron, right? So iron, cobalt, nickel, all these are examples of ferromagnetic materials. Okay, so I hope these differences are very clear. Okay, now moving to the next. Constructive interference and destructive interference. Okay, so you would have learned this in your interference topic. Okay, so we have two types of interference, basically constructive and destructive. Okay, so when a constructive interference is formed, when the light waves are in phase. Okay, so for example, if two waves are reaching like from two coherent sources. Okay, if a wave is reaching over here, now for example, here you can see 1, 2, 3 waves reached, and here 1, 2, 3, 4 waves reached. So what is the difference between them? The difference between them is one wave. Okay, so that means the waves are in proper phase over here. Okay, so whatever the light waves must be in a phase. But in destructive interference, now in case if I take a screen and two sources, okay, from one source, one wave, two wave, three wave reached. But from the other wave, from the other source, one wave, two wave, three wave, and 3.5 wave reached. That time they are not in the phase. Okay, that time what happens? The interference formed will be destructive in nature. Okay, if they are in phase, they are in what? Constructive in nature. And whereas, yes, as they fall on the screen, what happens? The intensity will be maximum and a bright bands or bright fringes are produced in constructive interference. So that's you can take. Resultant intensity is maximum, whereas bright fringes are produced in the constructive interference. But in this case, what happens? Intensity will be minimum. Okay, that's the reason a dark fringe will be formed. Okay, so interference pattern is bright, dark, right? When bright band is formed, when they are in phase, that is when constructive interference happens. But next, what happens? The destructive interference will happen. So like this alternate bright, dark bands you can see in a interference pattern. Okay, fine. Next, conditions. Okay, this conditions I have taken in the differences itself. Okay, but it can be asked as a separately like a 2 mark question also. Please remember the condition. Okay, so condition for phase difference is what? For constructive it is 2n pi. Okay, whereas for phase difference for destructive is 2n plus 1 pi. Okay, one you remember how these two are related means path difference. Okay, the path difference I'll take it as delta x. Path difference is always equal to lambda by 2 pi times phase difference. Okay, phase difference is denoted by phi. Okay, so when you substitute, you get lambda by 2 pi, where what is 5? 5 is 2n pi. Okay, so 2 pi gets cancelled. You will get n times lambda. Okay, that's how you get the path difference, and this is the relation between path difference and phase difference. Okay, so please remember this formula. Okay, so that time easily you can do for this also. I want you to try for this one. Check whether you will get it or not. Okay, so please try this. So remember the phase difference. Phase difference here is 2n pi. There it is 2n plus 1 times pi. That's it. Okay, so these are the differences between constructive and destructive. Okay, next I've taken a differentiate between interference and diffraction. Okay, so interference is what? Interference is superposition of waves. Okay, like when two or more waves, like when they combine, a band will be formed, right? That's what you call it as interference. Okay, but whereas in a diffraction, here a diffraction occurs when there is a bending of light around the corners of the obstacle. Okay, see now any obstacle. Now, for example, I've kept a pen over here. As the light falls on it at the edges, okay, at the edges it will bend. Okay, that whatever the pattern is formed on the screen, right, that pattern is called as diffraction. Okay, so this point you can take over here, and here the fringes are equally spaced. So now if you are getting bright dark band, you can say that the intensity will be the same throughout. Okay, like this is a pattern what is formed. Okay, so bright band, dark band, like that. So where it is equally spaced, that fringe width will be equally spaced. But in case of a diffraction, they are not equally spaced. Only at the center it will be maximum. As you go away from the center, what happens? The intensity will also be diminished, whereas the fringe width will also will reduce. Okay, so that's the reason we say fringes are not equally spaced. Okay, and here you need a double source. Okay, you need a two slits. You can observe this pattern just by take one cardboard sheet, make a two holes, and just leave one like a torch or something, and observe the pattern on the wall. Okay, easily you can see the interference pattern. But diffraction pattern is quite difficult to observe. Okay, but here, as I said, here they need two sources, two coherent sources. Okay, that's the reason I said make two holes. So when you allow the torch to fall on it, both will act like a coherent source. Coherent source means what? They both are having same wavelength. Okay, that's the reason. But here only single slit is enough. Single slit means a hole or a obstacle, anything you can take it over here. Okay, so these are the differences. Next, moving to the differentiate between conductors, insulators and semiconductors, very simple it is. Okay, conductors means what? Which will allow the charges to flow through them, and insulator is which will not allow the charges to flow through them, whereas semiconductor is something which lies in between conductors and insulators. Okay. And yeah, example for conductors, it is copper. Example for insulators, glass, plastic, anything you can take. Whereas example for semiconductors, it is silicon, germanium, all these you can take it. Okay, and you can say since it is high conductivity, therefore it will have a less resistivity, where we know that conductivity is reciprocal of resistivity. So if it has high conductivity, it will have less resistivity. If it has less resistivity, less conductivity, then it will have a high resistivity. But here resistivity will lie in between conductors and insulators. Okay, this you have learnt in your lower classes also. Next, moving to the intrinsic and extrinsic semiconductor. Yes. So yes, this is the most expected question. Okay. So this can be asked as a 2 mark, 3 mark also. Like they might ask you, explain the types of semiconductors. Okay. We have two types of semiconductors. One is intrinsic semiconductor. The other one is extrinsic semiconductor. Okay. So in intrinsic semiconductor, what it is like, it's a pure semiconductor. Okay. Like silicon, germanium, whatever we are taking, that's an intrinsic semiconductor. Okay. So as it is a pure semiconductor, it don't need any impurities. That's the reason we call it as a pure semiconductor, where here we can see that of course semiconductor charge carriers are holes and electrons, right? So here the number of holes and number of electrons are equal. Okay, there is no differences. How much of a holes are there, that much electrons will be there. Okay, so that's the reason we call it as pure semiconductor. And example you can take like silicon, all these are example of intrinsic semiconductor. Okay, but whereas extrinsic semiconductor is something like you're doping it. Doping means what? Adding impurities. Okay, so you will add the impurities to the intrinsic semiconductor. That time what happens, that intrinsic semiconductor becomes the extrinsic semiconductor. Okay, so doped with impurities, they are saying. Impurities means what? Like we add a pentavalent impurity, trivalent impurity, you might be knowing that. So adding impurities is called as doping. Okay, and those impurities are called as what? Dopants. Okay, so remember this. And here they are not equal. Number of electrons are not equal to number of holes. Okay, so we know that if electrons are more, then we call it as N-type semiconductor. If holes are more, then we call it as P-type semiconductor. So that's the reason this is divided into two types of semiconductors, P-type and N-type. Okay, so based on the number of holes and electrons, we are dividing it into two types. Okay, and then in case of intrinsic and extrinsic, which might have a more conductivity? Yes, it's an extrinsic, right? That's the reason we are taking extrinsic. If not, we would have settled for intrinsic semiconductor. But we need more conductivity, right? That's the reason what we are doing. We are using the extrinsic semiconductor. Okay. So yeah, that's a difference between intrinsic and extrinsic. Next, moving to the P-type and N-type. Again, as I mentioned, these are two types of extrinsic semiconductors. Okay, so we have P-type and N-type. So the name P tells P is something like positive. You can think like that. Okay, N is something like negative. We can consider like this. Okay, so for a P-type, we are doping with what? Trivalent impurities. That means the valency is 3 for this. Okay, so we are doping with trivalent impurities. Okay, where holes are majority charge carriers. That means the number of holes is more than the number of electrons. Since hole is something positive, right? So for P-type, number of holes is more than the number of electrons. Like that you can consider. So these are majority and electrons are minority charge carriers. So boron is doped with silicon. So boron is a trivalent impurity. You are doping the silicon. So that can be the example. Similarly, what is N-type? N-type is something you are doping with pentavalent impurities. Okay, so pentavalent impurities like phosphorus, all these you can consider as an example. Here, the name itself tells it's a negative, right? Therefore, number of electrons is greater than number of holes, where we can say that electrons are majority charge carriers, where holes are minority charge carriers. Okay, so therefore, the example is phosphorus doped with silicon. Okay, yeah, that's it. Now, moving to the last question. Okay, so differences between nuclear fusion and nuclear fission. The name itself tells fusion means what? You are combining, where lighter nuclei will combine to form a heavy nucleus. Okay, but fission is what? Heavy nucleus will split into two or more lighter nuclei. The name itself tells that. Okay, fusion is something combining, fission is splitting. Okay, so fusion means, remember the example of sun. Okay, and the nuclear fission means you can remember the nuclear reactor or atomic bomb, all these things you can remember. Okay, so now considering the sun, of course, the sun, its temperature is so much, right? So we can say it requires very high temperature. In that way, you can connect it. Whereas here, it can occur at ordinary temperature also. Okay, and then this, can you control the sun, whatever process happens? No, right? So we can say this, it cannot be controlled. Okay, but in nuclear fission, yes, it can be controlled. Okay, it can be a controlled reaction. And then the working principle of what? Hydrogen bomb. Okay, so remember, as I said again, sun, remember the elements of sun like that, hydrogen, all that. Okay, so it works on the principle of what? Hydrogen bomb. Whereas here, it works on the principle of, it's a working principle of what? Atomic bomb. Okay, example for this is sun, whereas example for this is what? Nuclear reactor. That's it. Okay. So these are the differences. Okay, so these are some of the differentiate questions. I think I've covered everything. In case if I have not covered, please let me know. Okay, so thank you for watching. Please like, share, and subscribe our channel so that even we proceed with a very good content. Okay, thank you so much.